All right. So now that we know what we can do, what the rate of a reaction is, and we know that if we have a low activation energy, a reaction will go faster, and we know the things that we can do to change the rate of the reaction. We could change the temperature, we could change the concentration, or we can add a catalyst. Now we're going to take a look at what happens to a reaction once it gets to a certain point. It starts to go in reverse. You saw that in the previous video where we were looking at the chemical reaction and the graphical representation. We saw that reactants were being made at the same time as products. So what is this? Before we go on to explain anything else, I want you to take a moment to view this problem, answer the question, and we will go over this when we meet for our lecture and practice session. So pause the video, try to solve it, and we'll get the answer in class. All right. So what is a reversible reaction? A reversible reaction is one in which the forward and the reverse reaction occur at the same rate. And if you notice from the simulation, once we started making product molecules, they started interacting with each other to form reactant molecules. Well, that makes sense because remember, concentration is going to affect the forward rate. So if I start adding more and more products, they start bouncing into each other as well during the reaction. So it's likely that if we end up with enough product, it's going to start reforming reactants. So if we take a look at this reaction, we have a forward reaction in which we have hydrogen plus iodine gives us hydrogen iodide. And the reverse reaction is which we have hydrogen iodide giving us hydrogen and iodine gas. So there's two rates. There's a forward rate, how fast I make hydrogen iodide, and there's a reverse rate, how fast I make hydrogen and iodine gases, right? So there's two rates, one going forward and one going in reverse. And we know that as we make more and more product, it's just going to shift the reaction reverse to start making reactants. Now, how do we get a reaction to go all the way forward? We use, remember you did calculations with theoretical and actual yields. Well, if we have a reaction in where we consume all of one reactant, we're likely to force the reaction to go forward. However, if we start with equal amounts of reactants and products, we're going to end up with a forward and a reverse situation. Okay? So, a reaction is going to reach equilibrium when one of two things occurs. The rate of the forward reaction is going to be equal to the rate of the reverse reaction. So when we are forming product molecules, when that rate becomes equal to forming reactant molecules or particles, we end up with equilibrium. So I am making reactant and product at the same rate, the same speed, right? And they're going to, these forward and reverse continue at the same rate until the system is disturbed, right? We get to the point where we have too many product molecules and we start making reverse. We get to the point where there's too much reactant molecules, so we start going back forward and making the products. And then we'll set up equilibrium. Then we end up having too much products and it goes back in reverse. And we set up another equilibrium. So it's dynamic, it's constantly moving. And the concentrations, however, at equilibrium are constant. Notice that in the last video, I was saying that at certain points in that reaction, reactants and products, they're constant. They stop moving, and then they start moving again, and then it stops, right? The bar graph was changing. And once it Once it was steady for a while, the system was at equilibrium. Then it starts changing again, and then it's steady for a while and it reaches equilibrium. There's a point in which we know what equilibrium is, and we'll talk about that in a moment. So how do we know? By looking at the rates of reaction when equilibrium is set up. Well, initially in a reaction, the rate of losing reactant is steep, right? Initially occurs very fast, right? We have high concentrations of reactant, low concentrations of product, and the initial rate at which I change from reactants to products is steep. It's fast. Then we get to a point where it levels off. That rate levels off. Initially, we have no product, and the rise in product occurs quickly to a degree, and then we get to a point where the concentration, or not the concentration, the rate of forming product and the rate of forming reactant become equal. How fast I get rid of reactant and how fast I form product becomes equal. Rate at which I lose reactant and the rate at which I gain product becomes equal. So equilibrium occurs when the rate of reactant depletion is equal to the rate of product depletion. The rates of forward and reverse reactions are equal. So when the rates of the reactants forming products and using up reactants is equal, we're at equilibrium. Another way to look at equilibrium is when there are no further changes in concentrations. If we're looking at concentration on our y-axis, at the beginning of the reaction, we have high concentration of reactants, low concentration of products. We rapidly lose reactant, rapidly gain product. It gets to a point where the concentrations no longer change. And at the point in which the concentrations no longer change, then we are at equilibrium. So once again, back to the simulation, it was when the reactants and the products, the bar graphs were constant. When they were moving, the system was not at equilibrium. When they were constant, then we were at equilibrium. When they were constant, we were at equilibrium. Okay?